Hello guys, time for me to do the flip assignment for AP Physics. I watched the two videos and then comment on them. Let's get started.
I'd like to dedicate this video to Lou Reed, who just died yesterday. This video is about circles, and although you may like circles, you know, tape comes in that shape and such, they are completely unnatural. Circles are really weird. Take, for instance, this trucker. I have a trucker here, and unlike most truckers, if you push down his head and let go, he'll drive away. That's cool. See this trucker? You push down his head and let go, and he drives away. And I like to ask my students, how can I make the trucker go in a circle? And sometimes they say, pull the string's wrapped around his neck. This is not something you should do with a real trucker. But if I pull the string and push down his head and he drives away, he just stops driving. He can't get away from me anymore. Now, that's not really cool. What is interesting, though, I'm kind of being a punk, how would we pull the string to make this trucker go in a circle? Like that? That's interesting. He's facing that way, but I'm pulling the string down. So what do you think he's going to do? Well, he's not going to be able to go straight, so he starts to turn. Whoa, easy now, trucker. How about that? Like that? Yeah, try again. And what I'm noticing is he's turning in a direction. Oh, that's very interesting. He's turning around in a circle. I took this from my son. It's not exactly perfect anymore. But what I'm noticing is that when he's going one direction and the force is going in a normal direction to that, let's see if we can make ourselves a little sketch, then the
I should have done that.
I'd like to dedicate.
Okay, let's keep on going.
Well, he's not going to be able to go straight, so he starts to turn. Whoa, easy now, trucker. How about that? Like that? Yeah, try again. And what I'm noticing is he's turning in a direction. Oh, that's very interesting. He's turning around in a circle. I took this from my son. It's not exactly perfect anymore. But what I'm noticing is that when he's going one direction and the force is going in a normal direction to that, let's see if we can make ourselves a little sketch, then the trucker turns. So here's what I've got. I say, if I want a circular path, then I could put a trucker right here and say that the instantaneous velocity of the trucker is that direction. And I might even call that the tangential velocity. Tangential is a nice word, fun pronunciation. Tangential. Oh, look, I see the word tangent right there. Yeah, tangent means that there's this line that's kind of barely touching right there. Sure, so that's a tangent line. This is pronounced tangential, and it's the direction that is in a tangent direction to the circular path. And then the thing is, the string was always pulling the trucker inward. And if you take Latin, then perhaps you've learned another word for inward. Maybe we can think of another word for inward. But I'm going to say that this force is always pointed inward. So if I make another, like a phantom truck right here, phantom ice cream truck, anybody with me there? Then I might say, well, let's say this is uniform circular motion, so it's not going to be speeding up or slowing down. Then the tangential would be that direction at that time. Notice that it's still tangent to the circle, so at all times the velocity is telling us where the truck is about to be, so it goes from here to here. But notice it had to turn a little bit, and the direction it turned was always inward. So I'm going to draw that force again towards the center of the circle. And it's time to review your Latin. Towards the center of the circle means centripetal. Maybe I should say centripetal means towards the center of the circle. This root right here is, of course, the center. And this root right here means to seek. So it's center seeking. A center-seeking force is a force that points towards the center. So when I say towards the center, I could just as easily a centripetal. So there is a centripetal force. In fact, there must be, because things don't like to move in circles. Things like to move in straight lines. If you fully understand
I don't.
Newton's first law, if you understand this, then you will believe with me that circles are utterly unnatural and require not just a force, but a force that is continuously changing its direction. Now that's interesting. I got a little challenge for you. Here's the challenge. Here are 5 situations where things are going around in a circle. And I want you to think of the reason those things go around in a circle, because you know that Earth would rather go in a straight line, and the lasso would rather go in a straight line, and a kid would rather go in a straight line, even when they're in a barrel of fun kind of Tom's Twister kind of ride. And a car would prefer to go in a straight line, but you can make it turn on flat ground. So why does it turn, etc.? Why could it go in a circle? And the car also likes to turn even, a steeply banked slope. We might even have no friction at all, but the car could still turn. And that might be for a different reason. So those are challenges I want you guys to address. Tell me the reason that all of these go in a circle, because circles are so unnatural they require a justification. What if this truck were right here? If the truck were right here, it'd be going that direction. That'd be my tangential speed, and it would be accelerating. It would be accelerating this direction, and I'm going to write F sub c right there for centripetal force. And guess what? Centripetal force is a net force. Centripetal force is a net force, and so I should never draw it on a free body diagram. Hang on, Doc, did you just draw centripetal force on a free body diagram? No, this is obviously not a free body diagram because it's got velocity on it also. This is just a sketch of what happens when things go in a circle. So centripetal force is a net force, which means cool things like if the net force is a centripetal force, then that's going to be mass times the acceleration. But guess what? If the acceleration is in the direction of the net force, which is in the direction of the centripetal force,